Mutually exclusive events versus independent events. So we are taking both these topics together because these are two concepts where students mainly have a confusion on and they mix up together. So let us take both these together so that we clearly understand what is mutually exclusive, what is independent, and how these two are different, right? So mutually exclusive events and independent events. Let's first take mutually exclusive. In mutually exclusive, occurrence of an event A prevents the occurrence of event B. Then A and B are said to be mutually exclusive. What did I say? If you know that event A has occurred, then you know for sure that event B cannot occur. Occurrence of A prevents the occurrence of B, or vice versa. That is, if you know that B has occurred, then A cannot occur. That is, only one among A and B can occur. Let's take an example. Let us say A is an event that you are presently in, let's say, France. Okay, you're presently in France. And let's say event B says you are in India. Can these two occur together? Can you be in India and France at the same time? No. So these two are mutually exclusive. If you are presently in France, then you cannot presently be in India. And if you are in India, you cannot be in France. Only one among A and B can happen, right? So how do you identify two events that are mutually exclusive? What happens if they are mutually exclusive? What is the condition? That is, if you know that probability of A intersection B is 0. That is, the probability of A and B occurring together is 0, then A and B are mutually exclusive. This A intersection B, this can also be written sometimes as P of AB. Both these are one and the same. This just means probability of A and B occurring together. So any two events for which both of them cannot occur together, or pictorially if you want to represent, if this is an event A and this is an event B and there is no intersection between A and B, that means both of these cannot occur together, then they are mutually exclusive. That is, normally if you draw two events, if this is A, then this will be B, which means either A can occur alone or B can occur alone, or A and B can occur together. So all these possibilities would be open in case of normal events. But in case of mutually exclusive, there will be no intersection between A and B. That is, either A can occur alone or B can occur alone. They cannot occur together. This intersection part, this is missing here in mutually exclusive, right? Let's see what are independent events. Independent events. In case of independent events, occurrence of one event does not affect the occurrence of A. That is, if you know an event A has occurred, you have no information at all about event B. That is, A's occurring or not occurring does not affect B at all. B may occur, B may not occur. This has no influence on A. That is the thing. This is independent. So independent and mutually exclusive are kind of totally opposite concepts, because in mutually exclusive, A totally influences B. That is, if you know A has occurred, the occurrence of B is clearly determined after that. You know it cannot occur if A has occurred. In case of independent, if you know A has occurred, that provides no information at all about the event B. It can occur, it cannot occur. It's totally dependent purely on B. In this case, A and B are independent events. So what happens in this case to intersection A and B? That is, what is the probability of A and B occurring together? How do you identify an independent event? In this case, probability of A and B occurring together would be is equal to probability of A into probability of B. How is this true? I told you that in this case, A and B are totally independent. For example, let's say A is an event that you tossed a coin, right? You tossed a coin. And let's say B is an event then that you rolled a die. Okay. Let us say you got a head while you toss the coin. Does this have any influence on what output you'll get while you roll a die? There is no influence at all, right? You may get 1, 2, 3, 4, 5, 6, anything. You may get anything, but this has no dependency on whether you get head or tail while tossing a coin first. So these two are independent events, irrespective of whether you get heads or tails while you toss a coin. When you roll a die after that, you may get any of these. The information about what is the output of tossing a coin has no influence at all. So A and B, they are independent. And how is this result true? That is, how is probability of A intersection B same as P of A into P of B? We had previously seen that P of A intersection B, this can be written as probability of B given A into P of A, right? This is the way you write, or you can also write it as P of A into given B into P of B. Both are one and the same. Okay, this or this, both forms are the same. Let us take this form. So here P of B given A into P of A. What is P of B given A? That is, given that A has occurred, what is the probability of B's occurring? What did we just say about independent events? In case of independent events, P of B given A is same as P of B. That is, whether you take just simply you take the probability of B, or you take the probability of B given that another event A has occurred, both are one and the same because A has no influence on the probability of B. So in this case, probability of B given A, this is equal to probability of B. So here instead of probability of B given A, I can substitute probability of B. So probability of A intersection B becomes probability of A into probability of B. So we already saw that P of B into A of A, P of A or P of A into P of B, both are one and the same. So in case of independent, this is the condition, and in case of mutually exclusive, we saw the condition is P of A intersection B equal to 0. So these are kind of totally opposite concepts.